We are getting our discussion started, and we're looking at a couple of things that are extremely important for us, or we are thinking, um, okay, we're thinking, right, determine the radius of convergence of the power series. We indicated last time that always for the radius of convergence, we use only one test, and it is the ratio test. Okay, so let's get started with this. So we agreed that we use what we call the ratio test. How do we use the ratio test in learning this? So we start as follows. So we let, right? So we should let A, N. Okay, we agreed it's in terms of R, but we change everything in terms of N. It's convenient that way. Right, N X to the power R, Y, N, it's a popular symbol, but it doesn't quite matter, right? And therefore, when we have these, then what do? We need to obtain the absolute value of the AN, right? In which case, therefore, you have the absolute value of 3 to the power n, right, times n times x to the power n. You divide everything by n squared minus 1, right? And then you get here 3 to the power n, and then you get n, and you get x to the power n. You divide everything by, you have the modulus of these. Okay, right, so this is true, but not only that is true, but it is true in conjunction with the an plus 1 term. Right, so the an plus first term is 3n plus 1 into n plus 1 into that n plus 1. You divide everything by n plus 1. You square this minus 1. So that we obtain. Right, so we proceed to simplify this. Right. So we obtain the following. All right, so we obtain the limit from the ratio test. The limit is the limit, right, as n approaches infinity of an plus 1 divided by the modulus of an. And this is the limit as n approaches infinity of an plus 1. Right, and the limit of an plus 1 is the same as what? Right. Okay, we continue. We continue. So this one is going to be exactly 3n plus 1 into n plus 1. And then we have the modulus of n plus 1. Right, so we divide by n plus 1. You square this one, we minus. Then we divide by the an, so it's like you are simultaneously multiplying by the reciprocal of the an, in which case, therefore, it is 3 to the power n, then it is x to the power n. And therefore, this is the limit as n approaches infinity of, right, so you have 3, because the 3 to the n cancels 3 to the n, right? And then now, what else do we have? Okay, obviously, we have a closing absolute value sign there. So 3 to the power n denominator cancels the one at the top. And then we have something here. We have n plus 1, which is divided by n, like that. And then we have what? Right, so it's dealt with the 3 power n, we dealt with the n plus 1. We have the n squared. Right, so we have the modulus of n squared minus 1, which you divide by the modulus of n plus 1, which you square, you subtract 1, like this. So you have divided the n squared minus 1 by something similar. And then you have one more thing to consider, the x to the power n modulus divided by the modulus of x to the power n. So that one is just only the modulus of x that is left. Okay. Next, we continue to simplify these. Right. Okay. Okay, so you continue. What do we get out of this? Um, right. So what we are able to obtain out of this is that we have the limit as n approaches infinity of the 3, right? And then we have 3 plus 1. Uh, we have n plus 1. We divide by that. Right, out of this here, you can even remove this thing, but obviously we need to be very careful to remove the absolute value because the value of r, similar to the value of n, begins from 0. If n is 0, we have 0 minus 1, 0 squared minus 1, which is negative. So we will maintain the absolute value there. But very important, the absolute value is in the numerator and denominator. So you can put one absolute value that's big and just manipulate the inside of this. So in each case, therefore, we can divide straight away by n squared, which is 1 minus 1 over n squared. You divide everything by it. You have this one, which is exactly n plus 1 over n. So you divide everything by 1 over n squared, and this is, you divide by n squared, both the numerator and the denominator, and then you have the modulus of these, from which we're able
Hello?
to, yes, please?
I'm confused at this part.
Okay, that part, right, okay, good. Right, so in view of the ratio test, we divide a couple of things, right? So we divide, um, um, we divide what? We divide an plus 1 by an. What is an plus 1? Okay, so, um, so an plus 1, do you agree that an plus 1 is all these here? Is 3 to the n plus 1 into n plus 1 and the modulus of that. So which is exactly written here. The bottom of the an plus 1 modulus, it's this one. But we divide by an. So if you divide by an, because an is a
Hello?
fraction. Yes, please.
Yes, I understand this.
Okay.
I
Yes.
don't understand how you got this solution.
The n squared minus 1, right? Right. So obviously, because we're dividing by an, we're multiplying by the reciprocal of the modulus of an, which is this one. So we're multiplying by this. Okay, so if you multiply by that, it is the modulus of n squared minus 1 divided by 3 to the power n times n times the modulus of x to the power n. Okay, are you able to see that?
Yes, I understand that.
Okay, now when you come to this, we look at the following. So let me come here and just alter the color. So for example, you can come here, and when you come here, you realize that 3 to the power n will cancel 3 to the power n, leaving us with 3 to the power 1, which is this one. Next, we have the n plus 1 in brackets, which is going to be associated with the n in the denominator. I've just done that. So I'm grouping like terms, right? So now we have this modulus of the n squared minus 1, which is this one. We divide by the modulus of this one, which is exactly that. This x to the power n modulus is going to cancel that, leaving us with only modulus of x to the power 1, which is this one there. Okay. Right. We continue with the simplifications. I just divided at this point by n squared for the numerator and denominator. So here is 1 plus 1 over n. Then now you have 1 minus 1 over n squared. You divide everything by what? Okay, here you can simplify this and have 1 plus 1 over n. You square this, here. So this is n, and that is n. And then now you have minus 1 over n squared. Minus 1 over n squared. Right, minus 1 over n squared. Right, so we have this. Okay, we have this. So you continue. Okay, we continue right now. And then now we have here the modulus of x. It is sure that is clear to some extent. Okay, right, if that is not very clear. Right, so we have this. We have this. So this one is 1 over n squared. This one here is over n. You close the bracket like that. So this one is n squared. Okay, right. Upon careful analysis of this, we're able to understand what the result is to this. What the result is to this. So, okay, we can divide the whiteboard like this and come all the way here. At this point, we write the limit as n approaches infinity of, now if you take the limit of this as n approaches infinity, what is the limit of all these? Thank you. Right, so it's just going to become, this is exactly the same as 3 into the modulus of x, because this is going to be 1. This is going to be 1 over 1. So it's 3 times 1 times the modulus of x. So the answer is 3 into the modulus of x. Okay, now, what do we obtain out of this here? Right, for convergence, we require, all right, what do we require? The ratio test says that for convergence, we require that. Right, 3 into the modulus of x is smaller than 1. So which means the modulus of x is smaller than 1 over 3. And this can be written like minus 1/3 is less than x less than 1 over 3. Okay, so, but always we need to just check the endpoints. So we need to investigate the 1/3, and we also need to investigate the minus 1/3 and check what's happening. All right, so we have this and we continue right now. Okay, I'm going to continue on the next slide. So we look at these very carefully and make sure that we understand what's happening. And make sure that we understand what's happening. So, right, and we are in business. We are in business, right? We are in business.
Hello.
Yes, please.
For this part, can you explain the modulus?
Okay,
Why this is?
yeah. Okay, the modulus. Yeah, the modulus will always be around the variables that can potentially be negative. So we can put the modulus around 3 to the power n, but the exponential function 3 to the power n is what? Is always a positive function. So it's just pointless for us to put the modulus there. Is pointless for us to put the modulus around what? Around the 3 to the power n, but also around n, because n begins from 0 to infinity. The summation The summation here is that this summation starts from 0 to infinity. So it starts from 0 to infinity. We can see therefore that it's pointless for us um, to put the modulus around 0 or any of the numbers from 0 to infinity. All right, so what does that mean then? It means therefore we do not put the modulus around the n is pointless. We can put it, but x is a variable, so the variable x can be negative because it's a real number, right? So as a consequence, we put the around the variable. Okay, so we put the modulus around x. Moreover, right, we put the modulus around n squared minus 1. Why? Because n begins from 0 and there's a minus there. That minus is enough of a threat because it is telling us that there can be negativity. So we're good. Right. So we're good to have the minus around the modulus around n squared minus 1. And then what else do we need now? Right. So we have therefore inverted the an. We just turned it upside down. Right. So we have managed to switch the numerator and denominator of the an because it is in the denominator of the an plus 1. Right. So, but now we're getting at the end that x lies between minus 1/3 and 1/3. Right. So we need to investigate this one. Right. Let's investigate. So we come here and say for x equals 1/3, we take the original series. Okay, you can take the original series. You can take it in terms of the everything 3 to the power r x to the power r. So here you have 3 to the power r x to the power r divided by right. What is it divided by? Divided by r squared minus 1. Divided by r squared minus 1. Okay. Divided by r squared minus 1. So what is this? Right. So this is exactly the same as what? It's exactly the same as the following. All right. So it's exactly the same as the following. So which is the same as infinity r to the 0. Right. So we have 3 to the power r divided by r squared minus 1. Right. And then here in the place of x is 1/3. So you put what? 1/3 there. Right, so let's just simplify this one quickly. Right, so you have the infinite series. And then now we have for this one, 3 to the power r is going to cancel, but I'm just going to write a trivial step. So this one is just 3 to the power r here, and this one is exactly r squared minus 1. Okay, from these, we're able to make the observation that the 3 to the power this, right? So we have the following, right? So the 3 to the power r cancels out. And therefore, what do we have? Right, so we have the following. Right, so we have the following. Okay, we have the following. Right, so we have the following. So we have the infinite series. Right, so we have r divided by r squared minus 1. Okay, so this is what we get. What kind of a series is this? And is this series convergent or divergent? That is the question we ask. Is it convergent or divergent, this series? Okay. And it takes us to the limit comparison test. right? Or any other test that can be very successful. So in this one, can you use any of these here? Because it vanishes. It vanishes. Okay. So, okay. What else to do? Right. So it's not alternating, so we can use any of the tests. We can use the P series test. For example, if you consider, right, so if you let Bn, Bn over n squared, we always do this. So it becomes 1 over n. And this is divergent. Is a divergent harmonic series. Right, so this one is a divergent harmonic series. Um, but now the limit comparison test itself must be determined. And we must actually determine that. So we are moving forward towards the limit comparison test just now. Um, right, we're moving forward towards the limit comparison test in just a split second. Right, so we're moving towards that in a split second. Is something I want to write. I'm going to write now the actual formula. I said it last time, but yeah, I'm going to write it again of the limit comparison test. Right. The formula for the limit comparison test is as follows. Right. So you remember that when you write the limit comparison test, you need to have a couple of things. It is there, obviously, in the study guide, right? So you have AN over BN. You have AN over BN, right? So um, let this one be, obviously, it's a divergent harmonic series, and right, consider the limit as n approaches infinity of AN over BN. This is the limit as n approaches infinity. Right, so I would be interested in this is what you need to learn, obviously, but you need to note that this is what the study guide shows, and the study guide is our main important resource. I'm going to give as well just now the page number in the study guide so that you can remember the page number in the guide. Right, so that you can use this limit comparison test for purposes of our studies here. Right, so right, the study guide was published in 2014 with a 2014 version of it. Right, so I'll just mention in parsing the idea of this series. Right, when you look at the limit comparison test, we say AN over BN. And now we look at the fact that this must not be 0. So, okay, this is the limit comparison test, exactly like this. Right, so this here is constitutes what you call the limit. So it's a test, comparison, comparison test. What does this limit comparison test say? Okay, it divides AN by BN. Right, so we have the AN. What is AN? AN is all these. So in other words, AN is N divided by N squared minus 1. That is AN. Right, so you divide by BN. So you divide by Bn and you divide by this. So if you divide by 1 over n, it's the same as multiplying by the reciprocal. So you have n and then you have n squared minus 1. Right, so you multiply by the reciprocal like this, and this is the limit as n approaches infinity of n squared minus 1, and this is 1. So you have that there. Okay, what do we realize?
Hello.
Yes, please.
I sent you the memo in the chat.
Okay, let me see. You said it actually in the chart. Okay, thank you. Let me see. Uh, okay, I'm looking. Thank you. Okay, I'm looking at it. Yes. Yes. Yeah. So it is exactly the same thing we've done, but ours is more correct than theirs. Ours is more correct than theirs because I'm looking at what they've done here. They have um they left out the absolute values around the a n plus one, yet they put the absolute values around the x. But they also got three modulus of x, in which case they got that divided by three like we did, and then they got that the modulus of x is less than 1/3, which is what we got. Right, so for convergence, now they said that this power series converges if it is less than one, which is what we said. I said for convergence, the three times the modulus of x must be smaller than one. Dividing by three meant that the modulus of x must be smaller than 1/3. It diverges if it's bigger than that. So it's okay to state the divergence part. Okay, so but it's just that it's not useful for us. Okay, so it's not useful um to state the divergence, but yeah, it's worth mentioning. Right, it's worth mentioning. So now look, the radius of convergence is 1/3. Okay, good. Thank you for obviously mentioning that. Let me see how far we've gone. Right. So obviously at this point, this question, to be more specific, asks for the radius of convergence. So we just went a little bit beyond that because obviously from this point, it is clear that the radius of convergence is 1/3. It's exactly the 1/3, which is what they got. Okay, but it's just that um, I was going on to determine the interval of convergence. So in other words, for the radius of convergence, we're done at this point for the radius. Okay. Um, but now I was continuing to determine ultimately the interval within which it converges. In which case, therefore, you can consider this for the interval of convergence, which is what the question normally asks. Okay. Right. So we're good. But I want to mention something. Um, okay, we'll continue. Okay, just one of my students. Okay, right, so we continue. We continue just now. Right, so now we note that therefore this here is different from zero. Right, since it is different from zero, it means a couple of things. Right. It means a couple of things. It means that um there is there is divergence because of the harmonic series. But this will be just for the interval of convergence, please. Right. But thanks obviously for noting that we are just going doing a bit much than required because it needed only radius 1 over 3. But now for x equals minus 1/3, it's going to be alternating. So you have the original series, which is r0, 3 to the power r, x to the power r, divided by r squared minus 1. And which is the same as this one here, r to the power 0, 3 to the power r, r, then minus 1/3 to the power r divided by r squared minus 1. Okay, so we continue. Okay, what are we getting here? What we're getting here is that we have the infinite series summation, that. So you divide everything, the 3, so you can separate this one, 3 to the power that, and then you have r squared minus 1, and then you have minus 1. You can write minus 1 to the power r, and you can write 3 to the power r. Okay, from this, we're able to achieve something. What are we able to achieve from this? All right, we're able to achieve a couple of things. Right, from this, we're able to achieve that the 3 to the r cancels out. And so we have this series here. Okay, we're doing the interval of convergence part. Right, so we have r divided by r squared minus 1, and then you have minus 1 to the power r, like this. Okay. So this one becomes an alternating series. For the alternating series part, you need to actually have a couple of things. You need to choose your Bn, right? So your Bn becomes everything else. Right, so, and then I'm gonna just mention that here in passing. So you would require, therefore, that at this point for the alternating series test, right? So you would have to realize something that you choose your Bn. So choose, right? So you choose, right? So you choose Bn, Bn divided by, you just leave the minus, n squared minus 1. Um, Now what happens here? So, but you'd have to have that, so that choose Bn to be that, so that Bn plus 1 is n plus 1 divided by n plus 1 squared minus 1. Right, so you compare these two things. If n is 1, which one is bigger? Okay, we want this to be decreasing, so for it to converge, for example. So you'd need um you'd need that right, you'd need something right, you'd need something. What did you need? Okay, if n is 1, this one is okay. We can't allow 1 because it's 0, the denominator. So which means that you'd have to uh, take um you'd have to take n equals 2, which is 2 over 3. So this one will be like 2 over 3. And here you allow 2, which is going to be 3 over. Okay, put 2 here, which is 2 over 3. Here you put 2, which is 3 over, and then here you put 2 plus 1, which is 3. You square 3, 9 minus 1, 8. Which one is bigger? Okay, I want to see if it's decreasing or not. Right. Right. So what do we get at the end of these? Okay, here we're getting 0. What? What is 2.3? It's approximately 0.67. And this one is approximately what? 0, comma 8 goes how many times there? It goes it goes 3 times because 8 goes into 24. Okay. So we're able to see therefore that if we divide this one, okay, one has to be a little bit faster. And because we're just doing something that is extra, and this one is not quite mandatory. Right. So if you do the 3 divided by 8, you can easily compare which one is which. So it's 0.35, 0.375. Right, so you can see therefore that Bn plus 1 is smaller than Bn, which means we have a decreasing um, Bn is decreasing. Right, so if Bn is decreasing, but also we require that the limit of the Bn as n approaches infinity, so you take the limit as n approaches infinity. Bn is this one, n over n squared minus 1. So you have n over n squared minus 1. All right, continue. Right. So we have this one. So what is the answer to this? Okay, this one is going to be exactly 0. It's going to be exactly 0. Okay, so we have that. Um, we have that. So it means therefore um this x equal to minus 1 over 3 is actually the at the convergence part, so which means that we are able to do the following. We're able to draw a small little conclusion about the interval of convergence. So we have the interval of convergence. And the interval of convergence is what? So because we had that it was minus 1 over 3 less than x less than 1 over 3. Or it was the modulus of these less than 1 over 3. This one was the, yeah, for convergence, we needed this, right, for convergence. So with that, we're able to say the following. Um, the minus 1 over 3 is included for convergence and the other one is out. So this one is the interval of convergence, this. Okay, so we're done that question. Right, the next one we're going to discuss is this one, which obviously you brought to the desk. Right, so you have this. Determine if the function is bijective, and if so, determine the inverse. Right, so right, so we have this. Okay, we have this one. Determine if the function is bijective, and if so, determine the inverse. The bijective function, first and foremost, is, well, the word bi means two, so it must be one to one, and it must be onto. Okay, right. So what does one to one mean? What does one to one mean? Right. So I'm sure that you've seen a couple of ways to think about what we call a one to one map. Right. So now the one to one function, you've already seen that part. It means that if ever, so we let for the one to one part, one to one. So we let g of x1 be equal to g of x2, and then we require to prove that this means x1 equals x2. But if gx1 equals gx2, what would it mean in terms of this? So there are two cases. There's going to be case one. You can look at it that way. Whenever x is not minus one, we have the top case. So that's going to be 2x1 minus 1 divided by x1 plus 1 is equal to 2x2 minus 1 divided by x2 plus 1. Okay, can you manipulate this and be able to get to some conclusion? Okay, it means clearly here, it looks very clear that x1 is going to be equal to x2, but we can just do algebraic manipulations. So we have this one. So we have this one here, x2 plus x1, 2x2 minus x1, x1 plus 1. So what is this? Is 2x1, x2 plus 2x1 minus x2 minus 1 is equals to 2x2 x1 plus 2x2 minus x1 minus 1. Okay, so let's see what you get here. Right? So minus 1 cancels out. The 2 cancels out. Um, Here what you have, you have 2x1 minus x2. So you have 2x1 minus x2 is equals to 2x2 minus x1. Okay, so what is this? So we can group the things. So it is 3x1 is equal to 3x2. And dividing both sides by 3 means x1 is equal to x2. Okay. So which means that for the case 1, when x is not equal to minus 1, it displays the one-to-one property. So hence, Hence, gx1, we're proving the bijectivity part. We don't determine if the function is bijective. So gx1, so hence if gx1 is gx2, then x1 is equal to x2. Or we can says write it like this and say hence g1 equals gx2. Hence g1 equals gx2. Um, implies that x1 is equal to x2. Okay, now there's case 2. What does case 2 mean to us? Okay, case 2 is the case where we have x is equal to minus 1. This one. So in that case, we let gx1 be equal to gx2. What would that mean? In that case, gx1 is 2 and gx2 is 2, so they are both 2. So that would mean that 2 is equal to 2. Right. Um, that would mean 2 is equal to 2, but 2 is equal to 2 at the argument of the function when the argument is minus 1 in each case. So it means that x1 is x2 is equal to minus 1. Okay, so gx1 equals gx2 means x1 is equal to x2. And therefore, and hence the function is 1 to 1. And so thus the function is 1 to 1. Thus the function is 1 to 1. Now, the next thing is to show that the function is onto. To show that the function is onto. Okay, so obviously we need to consider the domain and the codomain of the function for the onto parts. I remember trying to think of this even a while ago when I was assisting students. And I was thinking of the easiest way to even think of the ontoness of a piecewise function. But now this function obviously is nothing other than it has two cases, x not equal to minus 1, or the case x equals 1. We're asking the question, when will this be onto? Onto means I have a set of x values here, which we call the domain set. That's the domain. I have a set of x values here we call the range. Let's have points. So you can have points like this. So this function will not be onto because there's nothing that is coming here. Nothing. So this one is not onto. If it is onto, then if I pick an image, so now we're asking the question here, is this function in an onto function? We investigate. I would like us to Investigate that one. So we have G of R. We have the map G. Okay, it's easy. This one is not a difficult one, as it seems. And we have G of X. To X minus 1. X plus 1. If X is not equal to minus 1. 2 if X is minus 1. Okay. One way to see is to look at the graph of this function and analyze the behavior of this function. Okay, it's an easy one. It's a high school graph, this one. So it can be graphed with ease. This one is a rectangular parabola. Or what is this? And write like this over X plus 1. The slightly tricky step, this one. But you can divide like this. Right, so you have this minus 3 over X plus 1. 2 minus 3 over X plus 1. Minus 3 over X plus 1. The rectangular parabola with X equal to minus 1 is an asymptote. X equal to minus 1, but also it has Y equals 2.
Hello?
Yes, please.
How did you get this?
Okay, how did I get that one? I realized that 2 minus 3 is minus 1. But it was necessary because I wanted to, from 2x, I wanted to get x plus 1. So that it can cancel out with the x plus 1 denominator. So I realized that if I'm to put 2 minus 3, then I can factor out 2 here and have x plus 1, and x plus 1 is going to cancel. This is going to transform this into the high school rectangular hyperbola, whose graph we know very well. All right. Right, the rectangular hyperbola has the function a divided by x plus p plus q. So with this said, or with this mentioned, we're able to see everything here. We're able to see the A and the properties of the graph. So we're able to see also that the A is negative. So you have that here X is negative and then Y is positive.
For this question, is it necessary to draw the graph?
Yeah, that's a question. Yes, it is, so that you can be able to see the ontoness part. Because what are we investigating here? We're asking the question, is this function onto or not? It is easier to comment when the graph is been drawn. Right, when x is 0, for instance, here you'd have that y is minus 1. X is 0 here. G at 0 is minus 3 plus 2, which is minus 1. So when x is 0, y is -1. And that gives us the y-intercept. When y is 0, x is 1/2. When y is 0, x is 1/2. So the graph is going to cut here. Okay. Okay, we're looking at this graph here and we think of the two sets, the x set and the y set. Yeah, the y set. We're asking one question. Mm, what is the question? The question is that if I pick any real number because it's from R to R this function, if I pick a real number that is from the codomain, will I always get an x that is mapped to the y? Is there a y that is in the codomain that does not have an x that is mapped to it? That is just lying idle. That can potentially be only these points, only that point. The y equals 2 points. Because this function can never be, could never be 2, but this is taken care here. It's taken care of here. When x, this is a powerful function, this, because it's even take this top function would say the function is an asymptote at x equal to -1, and therefore it can't be -1. We can't have x equal to -1. But this is saying when x equals to -1, the function takes 2. So it's covering everything now. The function could potentially never reach 2 because that's an asymptote. It could never reach 2 because it's an asymptote. But now this is allowing it to say it can be 2 when x is -1. Or if x is -1. So in other words, hence f is on 2. Hence g is on 2. Since for every y, there exists an x such that g of x is equal to y is a element of y. So the this r is has any number you can pick here will always have an x that is mapped to it. So if I pick a y here, I'll always get an x that is mapped to it. So this graph here can reach all the y values on the, because now the fact that is here, it means that it's taking all the y values here, it's taking all the y values, taking all the y values up to 2, it's taking all the y values up to plus infinity. The only one it couldn't take was 2, but it's allowed to be 2. So this function is on 2. The graph illustrates the idea clearly. But this whole thing can be written descriptively in words, and one can explain why this function is certainly onto as well. Okay, we have not answered the question yet, except that now, in other words, hence or thus, G is bijective. He is what? Is bijective. Since is both one-to-one and onto. Okay, because they asked us to determine if it is bijective. But the graph, somebody might leave the graph out and just explain the behavior of the function and picking y values and arguing that for every y value, for the top part here, the function cannot be 2. It's not easy to see that the function cannot be 2 until you write the function like this and realize that 2 is an asymptote, and therefore the function does not reach asymptotes. But because it doesn't reach the examiner, the guy who came up with the question said, okay, we can allow the function to be 2 when x equal to -1, making the function to cover all. So now it makes this function to have the domain. Its domain now is all the real numbers, because ideally the only thing the function would not take here, it was saying x is not equal to -1, meaning the domain or set of x values could only be missing -1. We could not only allow x to be -1, but we allow it to be -1 there. So this function has both the domain and the range equal to R. So this function is bijective. But also we're asking the question, is it now when they can find the inverse? Okay, remember how we found the inverse last time because it's bijective. Since the function is bijective, then it's both one-to-one and onto. This is a powerful function, and that means, therefore, we can write the following. Right, we can write these and say it is G inverse of X. It means G of G inverse of X is what? Is X. So we have 2x minus 1 over x plus 1. If x is what? Is not minus 1, we have 2 if x is equal to -1. That's not what I'm saying yet, quite. Okay, because you see that it's not. Um, this is still g of x because I've written the x on the right. So I'm just going to just modify, but g of g inverse, because the function is now bijective, it means it's both one-to-one and onto, and it means therefore the inverse exists. Since g is bijective, it follows that the inverse exists. And this notation, if you take g of g inverse, then the result is going to be what? It's going to be, oops. So we have this, and therefore x now is replaced by that. So that's g inverse of x, g inverse of x, g inverse of x. G inverse of x. Every x is replaced by g inverse in the function. And this is necessary because now it is telling us that x is 2g inverse which is not equal to -1, 2 if that. So it is g inverse of x. You cross multiply. So you have this one here. which is x minus 2 is minus 1 minus x. So we have this one, okay? And then now, this is true, but also we require that x be not equal to 2 because it's going to be undefined this. For the other parts, we have from here, x equals 2. From the bottom, we have x equals 2. X equals 2 if g inverse of x equals minus 1. This is what we have. X equals 2 if g inverse is minus 1. Okay. Right. What is the meaning of this? Well, we are able to write the following. The g inverse of x can now be written like this. So g inverse is minus 1 minus x divided by x minus 2 if x is not 2. G inverse is minus 1 if x equals what? X equals 2. So that is the inverse. Okay, can we answer the question? Because determine if the function is bijective, and if so, determine the inverse. We've determined that the function is bijective, and then we've found the inverse. Okay, we continue. We continue. Now, next question. Mm, okay. Right, use a proof by contradiction to prove the following statement, to prove that the following statement is true. You may assume the well ordering axiom, right, which states every non-empty set of positive integers has a least member. Right, so we have that. We have that. Once again, it's a hint that you may assume the well ordering axiom, every non-empty set of positive integers has a least member. Right, so we're saying use the proof by contradiction to prove the following that the following statement is true. This one is greater or equal to that for all positive integers n. Right, so a proof by contradiction says that um, you say you assume you have a statement that has P implies Q. And so now you then assume that it is false. Assume that Q is false. Okay, so assume that P is true and Q is false. And arrive at a conclusion. Okay, so we're gonna actually say here for all positive integers n, for all n in the positive integers, or you can say for all positive integers n. In other words, if P then Q. So we assume that we have positive integers n. So assume, can we do this? Assume that for all positive integers n, we have, okay, for a proof by contradiction, we must just assume that this is not the case. Right, so if this is not the case, then it is what? We have that. For a contradiction, right. For a contradiction, we have the other way around. But we know that according to the well-ordering principle, every non-empty set of positive integers has a least member. So, which means, therefore, we can consider the least member in the set of positive integers. What is the least member? The least member is 1. So consider the least positive integer n, so that n equals 1. The left-hand side is 2 to the power n, which is 2 to the power 1, which is 2. The right-hand side is 2n, which is 2 into 1. So we have that the left-hand side is less than the right-hand side, because it means 2 to the power 1 is less than 2 times 1. And this is a contradiction. How is this a contradiction? Since 2 equals 2. Hence, hence the statement is true. 2 to the power n is greater or equal to 2n for all positive integers n. Okay, so we're done with this proof. Give the contrapositive of the following statement. So this one, contrapositive, we just remind each other. Right, by contrapositive, we mean that P implies Q is logically equivalent to not Q implies not P. That is the contrapositive. So if This one is convergent, so we have P. This implies this one is a null sequence, we have Q. So what is the contrapositive? The contrapositive is AN is not, can start with if. If AN is not a null sequence, then this series, now you must oppose the convergence part. This series is not convergent. This is just the contrapositive. All right, and we're done. We just put not, not. And then obviously putting not, not, then you can get an alternative words. You'll get an alternative what? You'll get alternative words. Okay. Okay, so we continue now and we look at more things. Right, the thing we're looking at right now is the next one. This question. So if here we're asking the question, we're asking this question, and the question is this rational? We did something like this, so we're gonna be faster. Use a proof by contradiction. Okay, yeah, it's a standard way of thinking this one. Right, so here you use a proof by contradiction. Use a proof by contradiction to prove the following statement. The square root of 5 is not a rational number. For a contradiction, assume that the square root of 5 equals a over b. A and b. All right. Assume that you can even say assume that you have a rational number there. Assume that the square root of 5 is a rational number. Is a rational number. Okay, if the square root of 5 is a rational number, so that is a rational number, so that is square root of 5 equals a over b, b not 0. A and b integers with a and b relatively prime. With a and b relatively prime. Okay. Thus, the square root of 5 equals a over b, and then we can square both sides, which means 5 is a squared over b squared. I'm going to be very brief here. And then this means 5b squared is equal to a squared. This is called Euclid's proof. Euclid's proof. Okay. A mathematician who lived. This implies that a squared is a multiple of 5. It's a multiple of 5. Right. Right. So if a squared is a multiple of 5, let me clean this up. Is a multiple of 5. Okay, this one. A squared is a multiple of 5. Okay. If a squared is a multiple of 5, what does it mean about a? A also must be a multiple of 5. Hence, it follows that A must be a multiple it follows that A must be a multiple of 5. Right. Follows that A must be a multiple of 5. That is A is equal to some 5k, k in an integer. K in integer. Okay, so we continue. We continue. Okay, so if it follows that A is a multiple of 5, that is A is 5k. Right, so if A is 5k, k an integer. Okay, we're moving faster. Right, so we continue and we have this. What we got at the end of this? Right, what we're then getting is the following. Thus, a squared can be written as 5 squared, which is 25k squared. So that now we take the equation 5, b squared, which is a squared. We have 5b squared and the a squared is 25k squared. We divide through by 5, which means it is 5k squared. And this means that b squared is a multiple of 5. And this means that in 10B is a multiple of 5. B is a multiple of 5. B a multiple of 5, it means that B is equal to some Bm where M is an integer. Thus, the square root of 5, which is the same as A over B, we said that A itself is 5K, but now we're coming and we're realizing that B is also 5M, which is that, so that um, A and B are not relatively prime. Are not relatively prime since they have a common factor. Since they have a common factor. They are not relatively prime since they have a common factor, namely 5. So we made an assumption. So the assumption is actually led to this contradiction. Therefore, we have a contradiction. A contradiction. That's our assumption. Our assumption that the square root of 5 is rational leads to a contradiction. Therefore, the square root of 5 is irrational. And therefore, the square root of 5 is irrational. And therefore, the square root of 5 is what? Is irrational. And we're done. Remember the question it said use a proof by contradiction to prove the following statement. That square root of 5 is not a rational number, and we've just done that for 6 marks. Right, give the negation of the following statements, and we'll remember what we said last time. We actually said when you negate a statement that says, right, for all x in U, the statement P of x is true. We said this is logical equivalent to the existential quantifier. There exists x in U, so you negate the existential quantifier, the universal quantifier. So you negate the universal quantifier. And then here you have the existential quantifier. And then you negate also the statement P. What is this? This means for all x in the interval minus 2, 2, you negate this. You have f of x is less or equal to 0. This is logical equivalent to the following. So you negate that, it means therefore there exists x, which is an element of the interval. And then not this would be bigger than 0. Okay, so we're done. This. The next thing, this one is what we just did now. So this question here has already been done. Solved. This one has been solved before. Right, move into the next one. Use the epsilon delta argument to show that this limit is 14. So this one you can start by saying given epsilon positive, we must find delta positive such that if 0 is less than x minus 2 is less than delta, then x squared minus 16 divided by x minus 4 plus 2x squared okay, plus 2x squared is less than epsilon. X minus 4 into x plus 4 divided by x minus 4 plus 2x squared is less than epsilon. Ah, I missed something. I missed 14. So you must transpose the 14 now and bring it to the other side of the function. So it's minus 14 less than epsilon. Now we start by looking at x squared minus 16 divided by x minus 4 plus 2x squared minus 14. X minus 4 into x plus 4 divided by x minus 4 plus 2x squared minus 14. Which means you have x plus 4 plus 2x squared. What is this? This is exactly 2x squared plus x minus 10. What are the factors of this? Which means it's 2x and x. We put 5 and 2. Negative, negative, positive, like this. 2x squared minus that. So this means you have the modulus of 2x plus 5, x minus 2. So 2x, you want to get an x minus 2 out of this. Another tricky step. So you must put minus that plus 9. So this is 2 into x minus 2 plus 9. So this is going to be less than 2 into 1 plus 9 into x minus 2. From this, we're able to see, therefore, that this is the same as 11 into x minus 2 is less than epsilon. And this means x minus 2 is less than epsilon over 11. For given epsilon positive, we must find delta. So delta now becomes the minimum of the two values, the minimum of 1. Okay, we chose 1 here because the modulus of x minus 2 is less than 1. But the modulus of x minus 2 is less than delta. So we chose delta to be 1. So in other words, at this point here, we can say we said choose the modulus of x minus 2 to be less than 1. So which means one value of delta is 1 was by our choice, but the other one now, because the modulus of x minus 2 is less than delta, but the modulus of x minus 2 is less than epsilon over 11. So which means delta is epsilon over 11 or 1. But it is the minimum of these. This is the smallest of these, depending on what epsilon is. So delta depends on epsilon. So this is the answer to the question. Right now, the time is exactly 18:46. I think it's a fair point to call it a good evening. And then we will continue tomorrow at the same time. Okay. And then I'm going to look at more things tomorrow. We'll look even at the corrections of the things we did last time and then a bit more concepts, etc., etc. Okay. And so for today, I must thank you for joining us. So you have these problems to practice. Well, how do you practice this in the at the moment you repeat, and then tomorrow I'm gonna bring more questions, practice questions, which I'm gonna load on the screen. I'm gonna load the questions on the screen, and then you can have the questions, okay? And then you can practice with the additional questions. But first things first, you first have to understand this. So you watch this video, you repeat these questions, okay? Right. So thanks a lot for joining us. Um, Um, thank you. I will see you again tomorrow at the same time, 4:30 p.m. All right.